Calculus video 14, limits to infinity. We are looking at what happens to the function value, to the y value now, as the x value goes either towards positive infinity or to negative infinity. So I have a drawing here. It looks more kind of like a rational function probably. And what you see there at y equals 3 is a horizontal asymptote, right? That dotted line there, y equals 3. And basically what we're saying is the curve gets close to that horizontal asymptote, typically as the x value goes towards negative infinity or positive infinity. And in fact, this idea of limit to infinity, limiting to infinity, is the same idea that you had back in algebra for horizontal asymptotes. It's what happens to the y value as the x value goes to either positive or negative infinity, and it typically for a horizontal asymptote, it gets the value of y, that the curve gets close to that asymptote. So for example, in this particular sketch, as the x value goes to, say, positive infinity, so positive infinity, as the x value gets large, gets very large, 10, 100, 1,000, million, right? What's happening to the y value is the y value on this curve is approaching a y value of 3. Right, a y value of 3. The curve is approaching a y value of 3. Therefore, what we say is this. The limit as x goes to infinity of this particular function is equal to 3. As x gets really big, the y value tends to 3. And in fact, in this particular case, it works both for infinity and negative infinity. Notice as x goes towards negative infinity on the left-hand side over here, the y value also tends towards 3. So we could say that the limit as x goes to negative infinity of our function is also 3. Good, so let's try some examples. Let's start with the limit as x goes to infinity of 2x squared minus 7x divided by x squared minus 9. Okay, so here's the thing we can think about it. If x is going to infinity, that means x is getting really, really big. Okay? If x is really, really big, pick your favorite big number. 100, 1,000, 10,000. I kind of like 1,000. And do a quick comparison here of the value of 2x squared versus the value of 7x when x is 1,000. Right? If x is 1,000, 2 times 1,000 squared, and then you have the 7 times 1,000. They're subtracted in between there, but the point is 2 times 1,000 squared. So that'd be 1, 2, 3, 4, 5, 6 zeros. Should be 2 million. Versus 7 times 1,000 is 7,000. As this x value gets even bigger and bigger, the difference between that, plugging in 1,000 into 2x squared versus plugging in 1,000 into 7x, keeps getting bigger and bigger and bigger. In fact, if you compare just the 1,000 to 1,000 squared is 1,000 times bigger than 1,000. Right? It's 1,000 times itself. It's 1,000 times bigger than 1,000. Point being this. If as x gets really big, 2x squared is much, much larger, that's a double greater than sign, is much, much larger than 7x as x goes to infinity. So think about this. 2 million minus 7,000. Yeah, you lost 7,000, but in comparison to 2 million, losing 7,000 is not that big of a deal. Right? And if you made that number 1,000 even bigger, 10,000, a million, a trillion squared times 2 versus 7 times a trillion, it becomes even greater of a discrepancy. What we can say is, yes, I have 2 million, and I'm subtracting 7,000, but that's basically the same as 2 million. Right? 2 million minus 7,000, not that big of a difference. Just call it 2 million. Same thing occurs in the denominator. Compare x squared and 9 as x goes to infinity. Again, as x is, say, 1,000, my favorite big number. So 1,000 squared is 1,000,000, and 9 is just 9. And if we take 1,000 and we subtract 9, we take 1,000,000 and subtract 9, it's still basically 1,000,000. If you have $1 million and you spend $9, who cares? Right? That's the idea here. As x goes to infinity, the important part about this problem here is not the 7x or the 9. The limit of 2x squared minus 7x divided by x squared minus 9 is basically the same as, not exactly the same as, it is basically the same as the limit as x goes to infinity of 2x squared over x squared. There's really not that much difference. The x squared term way outweighs the 7x term, and the x squared term completely outweighs the 9. If we're able to write it like this, then we see that the x squareds cancel, and this is equal to the limit as x goes to infinity of 2, which is just 2. And what we're saying there is, basically, there's a horizontal asymptote at y equals 2. That's our answer, by the way. That as x goes to infinity, the y value limits to 2. There is a horizontal asymptote at y equals 2. And as x is going to infinity, I'm not sure what this graph looks like, but as x goes to infinity, the y value will approach 2. Right? As x goes to infinity, the y value is going to approach 2. That is a limit to infinity. Notice a couple of things about, or one main thing about the original function that we're taking the limit of, this green here, is we started with 2x squared minus 7x over x squared minus 9. And if you remember back from algebra, we said that if the degrees of the numerator, the degree of the numerator, which in this case is 2, exponent of 2, degree is the greatest exponent, is equal to the degree of the denominator, again 2, if those are equal, then the horizontal asymptote will occur at the leading coefficient over leading coefficient, which in this case is a leading coefficient of 2, this coefficient of 2 here, divided by a leading coefficient of 1, which is 2. So we have a horizontal asymptote, we have a limit as x goes to infinity at 2. These are problems that you could be able to just look at and give me the answer. You could recognize that the degrees are the same, therefore the answer is the ratio of the leading coefficients, as long as x is going to infinity. Okay, what happens if the degrees are not the same? Let's consider this one, the limit as x goes to infinity of x squared minus 6x plus 11 divided by x cubed plus 1. Okay, so again, you're picturing x getting really, really big. Once again, if x gets really, really big in, let's say 1,000 or 1,000,000, whatever, 1,000 squared is much larger than 6 times 1,000, and it's much larger than 11. So the 6 times 1,000 or 6,000 compared to the 1,000 squared, which is 1,000,000, doesn't make that much of a difference. Similarly, 1,000 to the third compared to 1, that 1 is not going to make that much of a difference. So this is approximately equal to the limit as x goes to infinity of x squared over x cubed. And if I do a little bit of cancellation, this is equal to the limit as x goes to infinity. X squared cancels with 2 of the x's in the denominator. That gives me 1 over x. Now if I let x go to infinity, this is equal to 1 over infinity. If you divide 1 by a very, very large number, you get a very, very small number. 1 divided by infinity gives you 0. Right, 1 divided by 1,000,000, very small number. 1 divided by infinity, even smaller, goes to 0. So the answer to this one is 0. Two things to point out here. The degree of the numerator is 2. The degree of the denominator is 3. Anytime that denominator degree is larger, the limit as x goes to infinity of that particular function will go to 0. Second thing is what we created, and remember back from algebra, is when we have this situation, we end up with a horizontal asymptote at y equals 0. With our function, whatever it ends up looking like, approaching that horizontal asymptote. Okay, very good. Let's try another example. How about the limit as x goes to infinity? This time we'll go x squared plus 5 over x, let's make it 4x plus 10. Using the same logic that we had before, if you plugged in infinity or x gets really, really big, a really big number squared compared with 5, the 5 doesn't do anything. Same thing with the 10 in the denominator. This is approximately equal to the limit as x goes to infinity of x squared over 4x. Canceling, I can cancel one of the x's in the numerator with the x in the denominator. Therefore, I get the limit as x goes to infinity of x over 4. And as x goes to infinity, we have infinity divided by 4. That's still infinity. If you count forever and divide that by 4, you're still counting forever. It's still going to infinity. That's a little weird for some students, but you get used to it. Answer here is infinity. What we can see is that the degree of the numerator was 2, the degree of the denominator 1. So anytime the degree of the numerator is greater than the degree of the denominator, as x goes to infinity, the y value will also go to infinity. The picture here is not one of a horizontal asymptote, but one of a slant asymptote, where the curve looks something kind of like this. Let's take a look at a couple of these, but except not going to infinity this time, but going to negative infinity, and what would have happened. Let's just start with this one. What would we have if we took the limit as x goes to, say, negative infinity of x squared plus 5 over 4x plus 10? Okay, the same thing, we're going to say that's approximately equal to the limit as x goes to negative infinity, x squared over 4x. That simplifies to the limit as x goes to negative infinity of x over 4, which is negative infinity over 4, which is negative infinity. And that should match the graph that we've drawn here, that as x goes to negative infinity, the y value is approaching negative infinity as well. It's going down to negative infinity, down forever. Let's see if that same sort of thing happens on some of the ones we had earlier. So we had, let's try this first one. The limit as x goes to infinity of 2x squared minus 7x over x squared minus 9. 2x squared minus 7x over x squared minus 9. But this time, let's let that x go to negative infinity. Once again, we work this the same way, where this is approximately equal to the limit as x goes to negative infinity of 2x squared over x squared, which the x squareds cancel, and we get the limit as x goes to negative infinity of 2. Plugging in negative infinity to all the x's, well, there are no x's, so we just get 2. Notice the sign didn't change here, and we actually, what happened is we just have that single horizontal asymptote at y equals 2, and therefore from the right as x goes to infinity, or from the left as x goes to negative infinity, both of those limit to a value of 2. The third one, or the middle one we had, here, without doing all the work, you can see is going to be the same thing. We have one horizontal asymptote at y equals 0. As x goes to infinity, the y value goes to 0. As x goes to negative infinity, the y value also goes to 0. So that answer, if we limit that to negative infinity, would also have an answer of 0. Okay, how about a couple more problems? Let's do this one. How about the limit as x goes to infinity of 3 over x plus x minus 4 over x squared plus 1 minus 5. Okay, so 3 over x, you're thinking about letting infinity into the x there. 3 divided by infinity, that's going to go to 0. The middle term, let me work on the middle term here. This whole thing is approximately equal to the limit as x goes to infinity. I'll keep the 3 over x. But on the middle term, I'll write that as just x over x squared, subtracting 4 in the numerator, adding 1 in the denominator, is not changing x going to infinity, and then minus 5. Canceling the x with the x here, we get the limit as x goes to infinity of 3 over x plus 1 over x minus 5. Letting x go to infinity, that's 3 over infinity, plus 1 over infinity, minus 5. A number divided by infinity goes to 0, so that goes to 0, that goes to 0, and we get an answer here of negative 5. All right, how about one more? This one's interesting. Let's take the limit as x goes to infinity of the square root of 25x squared plus 11 divided by 3x plus 4. Now this one's a little strange, but we're going to use that same sort of principle that this is approximately equal to the limit as x goes to infinity. Square root of 25x squared plus 11. Adding 11 to a very, very large number doesn't change much, so we'll just call it 25x squared. And then adding 4, same thing, let's just call it 3x. What is the square root of 25x squared? Be careful. The square root graph, remember the square root graph, looks like this. Can the square root graph be negative? No, there's nothing over here for the answer to be negative. The square root of something is always a positive answer. I drew that incorrectly. Hang on one second. Erase my circle there. The answer to the square root, so we had to put in positive values, except for because it's squared, I can actually put in negative values as well. But the answer will not be negative here. The square root of 25x squared actually looks more like this. Hold on, that's poor. Let me try that again. Looks more like this. Because I can put in negative x values, like negative 2 squared is 4. 4 times 25 is 100. The square root of 100 is 10. All right, we can put in negative values, but none of it becomes a negative answer. So when you tell me the square root of 25x squared is 5x, that's almost right. It's actually, because it can't be negative, the absolute value of 5x. And this is where things get interesting. The limit as x goes to infinity of 5x over 3x. As long as x is going to infinity, that means x's will be positive. And if the x's are positive, the absolute value of 5 times a positive number, which is positive, the absolute value of a positive number is that same positive number. So because x's are going to infinity, therefore 5x must be positive. This is just equal to the limit as x goes to infinity of 5x over 3x. Right, we can remove the absolute value of 5x because the x's are positive numbers and 5 times a positive is positive. Canceling out the x's, we get the limit as x goes to infinity. That'll just be 5/3 left over, and therefore the answer is 5/3. Or if you like, 1 2/3. right, 1.67. In other words, the y values are limiting to 1.67 as x goes to infinity. And just to clarify, this graph that I've drawn here in green, that was the graph of y equals square root 25x squared, not the graph of my entire original function. Okay, what happens, though, in this case, if we have the limit as x goes to negative infinity of the square root of 25x squared plus 11 over 3x plus 4? Same idea. Limit x goes to negative infinity, square root 25x squared over 3x. Limit as x goes to negative infinity, absolute value of 5x over 3x. But now, our values are negative. The x values are negative. They're going to negative infinity, therefore they are negative. 5 times a negative number would be negative, the absolute value of which makes it positive. So our numerator would be positive, right? The absolute value of 5 times any number is the absolute value of it makes it positive. But if we want to keep the numerator positive but plug in negative values for x, this is equal to the limit as x goes to negative infinity of negative 5x over 3x. And if that seems counterintuitive, think about this. Pick a value as x goes to negative infinity, like negative 1,000. Negative 5 times negative 1,000 is positive 1,000, or positive 5,000. We're changing the sign back to positive because we're plugging in negative values of x. Then, when we cancel the x's out, we have the limit as x goes to negative infinity of negative 5/3, which is negative 5/3. Notice that's the different answer than we got when we went to positive infinity. This is one of those rare cases, and it has to do with that square root of x squared being inside of there, but this is one of those rare cases where we have two horizontal asymptotes. We have a horizontal asymptote at y equals 5/3 and a horizontal asymptote at y equals negative 5/3. And the function, as it goes to the right towards infinity, goes towards the positive 5/3, and as it goes to negative infinity, goes to the negative 5/3. You actually have two horizontal asymptotes in this case.